Hi there, I'm Amir, a PhD student from University of Warwick, and I'm here to present my latest work named Visually Aware Acoustic Event Detection using Heterogeneous Graphs. I'm also presenting this paper in person in InterSpeech 2020. Feel free to come. My session is a poster session on Tuesday. Finally, note that this is a collaboration between the University of Warwick, University of Glasgow, and Google Research. Perception of auditory events is inherently multimodal, relying on both audio and visual causes. Perceptual studies have also revealed that visual causes can even change how sound is heard. But the problem of using other modalities alongside with audio has two major challenges. First, finding the shared and complementary knowledge between modalities is hard, and then we have a temporal process here, and we should maintain a tight temporal synchronicity between modalities. So in this work, we propose to use a heterogeneous graph-based solution to mitigate the information problems. But you may ask, why graph modeling? We propose to model an audiovisual data with a heterogeneous graph because, first, heterogeneous graphs are a compact, efficient, and scalable way to represent data involving multiple different entities and their relations. Second, in these type of graphs, we can explicitly capture the spatial and temporal relationship between modalities. And finally, multimodal heterogeneous graphs lead to a closer coupling between concepts in multiple modalities, resulting in a significant performance improvement over various methods. In this work, we develop a graph construction method for converting an audiovisual clip to a multimodal heterogeneous graph. And then we also propose a novel heterogeneous graph neural network that can capture modality specific as well as complementary information between modalities. And finally, we evaluated our methods on popular audio set on acoustic event classification task. So in our framework, the first step is to construct a heterogeneous graph given an audiovisual clip. First of all, we divide each audio and video frames into Q and P overlapping segments respectively, as you can see in the right-hand side of the slide. After feature extraction from these segments, each of these Q and P frames features are associated with a heterogeneous node in a graph. This way, we only have nodes, but we still need edges. To do so, we consider two specific hyperparameters for each modality in order to add inter and intramodality edges, span across time, and dilation. The former denotes the number of nodes connected to each node in the temporal direction, whereas the latter denotes leaps between nodes. In total, we have 6 hyperparameters for graph construction. Given a heterogeneous graph with a set of V nodes, including audio and video nodes, in addition with a set of edges, including inter and intramodality edges. Consequently, we would have 3 different adjacency matrices for each edge type. In acoustic event classification task, each video clip and subsequently each graph is associated with a label, and the task is to predict the correct label indicating the acoustic event happening in the video. After having a heterogeneous graph, we need a graph-based model to process it, as the regular GNNs are not applicable on heterogeneous graphs. We propose our own framework. It consists of several heterogeneous graph layers, following pooling layers to extract graph embedding. You can see the heterogeneous layer in the right side. It has 3 different flows of data. 2 majors are audio and video flows. The last one is responsible to bring visual information and enhance audio perception. These 3 flows are independent of each other, which enables us to have different dimensions over each modality. As I already said, we evaluated our method on audio set. This dataset consists of 10-second video clips with 527 classes. We decided to select the first 33 classes that have high confidence score. For audio encoder, we used VGG-ish network to give us 128 dimensional vectors. And for video encoder, the S3D network has been used to derive 1024 dimensional vector. At final, we would have heterogeneous graphs with 100 audio and 40 video nodes. Here is the numeric results. We compared our method with several graph-based and state-of-the-art methods in mean, average, precision, and ROC-AUC score. We also reported the number of trainable parameters for each model at the most right column. In the first section of the table, we compared the performance of our model using single modalities, which is shown that the modality combination with our proposed intramodality flow is superior to each of them. We've also shown that the popular ResNet and LSTM performance with the same feature input as our graph-based model, and our model clearly outperforms both. But last but not least, in the last section of the table, our method outperforms the state-of-the-art models on this dataset. We also depicted the attention weights of our pooling layers for both cases, with and without visual assistance. In this first example, there is a motorcycle starting. Let's look at it. The video-assisted attention weights suggests that our model can capture additional meaningful patterns, such as the engine start. Furthermore, as the engine sound fades, the attention weights correspond to the audio-only model decreases, and the video-assisted attention weights have relatively higher values, indicating that the video information extracted by our model is complementary to the audio event information. In the next example, a horse begins nailing and moves away from the camera. As it moves, the sound fades. The horse is no longer visible or audible as time elapses. The audio-only model incorrectly detects these moments by assigning high attention values, while the audio-assisted model correctly discards these moments. So in this work, we propose a framework for constructing heterogeneous graphs from audiovisual data and modeling temporal and spatial connection within it. We further introduced a new graph neural networks, as the regular GNNs are not applicable in heterogeneous graphs. At the end, we also evaluated our methods on audio sets, doing acoustic event classification, and showed our superiority over graph and non-graph methods. Thanks for staying and watching this presentation. The code is available on GitHub, and you can contact me anytime asking your question or discussing our audio. Let me know what you think about my work. Also, feel free to come to my presentation session. It's a poster session on Tuesday, and I would be happy to discuss audio towards this kind of research.